Okay. So, good afternoon, everyone from India, and good morning to you, sir. And once again, warm welcome to the last and final day 4 of our webinar series, Understanding Reversibility, Edward Fredkin Memorial Lectures, organized by Cellular Automata India. So, today we are going to have two talks. First talk is the gift of invertibility in math, physics, and cellular automata by Tommaso Toffoli. And the second one is negation, absence, perception of absence, and reversibility by Smita Shorter. So our first speaker is Tommaso Toffoli. He doesn't need any introduction, but we'll introduce him anyway. Tommaso Toffoli is a professor of electrical and computer engineering in Boston University. He received his Doctor of Physics from University of Rome, Italy in 1967, and his second PhD in Computer and Communication Science from the University of Michigan, with the thesis on cellular automata mechanics in 1977. He joined the MIT next year, where he remained as a principal research scientist until 1995, when he joined the Boston University. He is an IEEE fellow, member of editorial board of several important journals. But apart from everything, he is a pioneering figure and advocate for reversible computation and the notion of invertibility, as he says it. So I remember when I started my PhD and was trying to work with reversibles here, among the first few papers that I started reading was your paper, Invertible Cellular Automata Review. I admit that I was not able to comprehend many things about it at that time. I don't know whether I'll be able to comprehend it totally now also, but it's a very interesting paper. His work on cellular automata mechanics, cellular automata machines with non-Margulis is a seminal work, which is on fine-grained architecture for massively parallel computation. He was a close associate of Edward Fredkin and introduced the Toffoli gate, which was later adopted as a fundamental logic primitive for quantum computation. So today we are honored and excited to have Professor Tommaso Toffoli with us. And we thank you, sir, for accepting our invitation. Now it's over to you. So you can share your slides if you want, or you can just start.
No, my speech will be a story, a mixture of stories of different people, including myself.
Okay.
You tell me when I could start.
Yeah, you can start. You can start.
Okay. Yes. Look, well, so I just said it. I don't want to give a lecture with a lot of formulas and a lot of references and other things like that. I will just articulate it like some sort of a merging stories and histories. Okay, let's start with something to set the environment. I was born in a post office. The story is this, that it was during the end of the war. My family was in Rome. My father was working with a Department of Health in Rome, and that building was very near to a railroad node, and so it was probably the first thing that the Germans would bomb next in order to prevent the wave of Americans that were coming north from Sicily to liberate Italy, so to speak. And but he had a wife and a very young daughter. She was 1 year old, 2 years old, something like that. So he decided to send my mother, his daughter, and me in pectore, or better, in utero, to a little village where he was born in northern Italy. And I ended up being born there. And now I would say a little story that will show how things connect with one another and get repeatedly. I said I was born in a post office. What happened is that my grandfather, who was living there in that village, was a well known and well estimated citizen there of that village. He had been a judge of peace and then municipal, in the municipal council and other things like that. At a certain moment, there was a problem that in the post office there were some problems in the books. So probably somebody had sold stamps and kept the money instead of putting them in the cash register, something like that. And so he was fired. And my grandfather, who was a very cultivated person, and I would say well known there. Well, at that time, the post office, the post officers was paid by the central government, but the locales, the building where the post office was had to be provided by the municipality. So my grandfather went to the mayor and he said, "Look, let's make a deal. I will provide just all of the locale for the post office, that the rooms at the building and so on, and you make me post office. Well, uh, the post office manager." And the thing was accepted because it was a very good deal for the village and a good deal for my grandfather. And so it ended up learning everything in telegraphy. And then he added a little cardboard cone to the arm of the receiving part of the telegraph, so that he could do his business and walk around and talk to other people and so on, and listen to that tick, 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 that for other people was just tick, tick, tick. But for him was dot dash all the time. And he could understand it so well that it's like if somebody was talking to him. So I was born in this environment. My first toys were rolls of telegraph tape and canceling stamps, okay, that kind of things. And now I want to say something for the things that get repeated and repeated in information science. This was a multi-village line, a telegraph line, about 60 miles long. But every time that somebody pushed on the key of the telegraph, the line got pulled down from 12 volts to ground. And all of the villages on that line, they heard exactly the same thing. And now, at this point, in order to prevent conflicts, the thing was like this, that the person who was operating the telegraph, the telegraph key, was supposed to know Morse code very well, so that when he went tap, 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 he was supposed to imagine what other people would hear from what he would hear. If what he heard was different from what he tapped, that means that somebody else was trying to grab the line. So that the rule was that at that point, everyone on the line will let go of the telegraph key and wait a small amount of time, but not always the same amount of time. And then somebody or somebody else will pick up, just like in a conversation at the party, that if somebody gets interrupted, other people may go in. Now, it turns out that is exactly the same algorithm that is used in the internet to avoid conflict. exactly, but instead of being administered by programs, it's administered by people that know that what they hear is different from what they transmitted, and so they will just stop and start again. All right. So this to just to give you a bit of an idea of how many things that we think that they're very modern have been thought over many times in different ways and realized in different ways. And something like this happened with cellular automata and with invertible computation. Now, to make a long story short, eventually I got a Fulbright grant for the United States. And eventually I started a PhD at the University of Michigan. And there I was given as an the first couple of years you take all of the courses and so on, you don't have an advisor. But when I came back from going to Italy and coming back to the United States, because the Fulbright grant wanted you to leave America for at least a couple of years before returning. They wanted to avoid that being an escalator for citizenship and so on. So when I came back and I started working on my research, on my thesis, I had as an advisor John Holland, who was one of the pioneers of evolutionary algorithms. And then I was joined as a co-advisor by Arthur Burks. Arthur Burks had been a collaborator of von Neumann. And eventually, von Neumann has started thinking of a way of doing self-reproducing mechanisms. He was very concerned with self-reproduction, as a family of Jews that have settled very well in Austria, in Hungary, and so on. But now they saw everything, falling apart because of the Second World War and the persecution of the Jews and so on. And so the problem of self-preservation, or at least self-replication, was an important one for him. This is what I imagine. And so he started thinking of doing reproducing structures, but he was thinking of just physical things, sort of a factory that had all of the supplies and all of the energy, so that you could make another factory like that one. But that was an enormous endeavor. Instead, his friend Stanislav Ulam, a very good mathematician, I met him and he was a very nice person, suggested, but why don't you do it, sort of virtually, by doing some sort of, by using a world that is like a checkerboard. And so, and that is what von Neumann decided to follow. He was a big genius of everything. He was interested in everything. And he was interested also in parties and in smoking and in drinking and in women and everything else. So he started having this structure. He called it cellular automata. And he started designing cellular automata rules and structures for a machine within the cellular automaton to replicate itself. And the interesting thing is that if the way that he found is directly, it was a few years before the discovery of DNA, but it was directly the same thing. That is, the reproduction was not done by this, that I take a caliber and I measure my nose and my eyes and so on, and I make copies of that. But that I don't want to copy my structure because it's very difficult, to do it well. I will have to make a hole in my head for the in the brain in order to know what is there. Instead, what you have is instruction for making the machine. And so you have to doing self-reproduction. The best way, it's not the only way, but best way to have self-reproduction is to essentially be made of two parts. One part of information, a long tape that says what to do to make you, and the other is you. Now, the you that is you will will make a copy of a tape that is extremely easy. And then with the tape, it will make a copy of you. So you alternate between these two phases. And this was what biological evolution does. So once it discovered, it managed to find a rather complicated rule with 29 states per cell, and that seems to work to make sort of a machine within the cellular automaton and a tape within the cellular automaton. Once it was convinced that the thing will work, he abandoned the thing and went to do all of the other things that they like to do. And the construction was completed by Arthur Burks, which was my co-advisor. Eventually, people found much simpler ways of doing self-replication in cellular automata, but that was the way that happens. You start in a complicated way, and then you simplify it, and you streamline it, and so on. So Ulam and Van Neumann are, around between the 40s and the 50s, developed the idea of cellular automata. Now, cellular automata actually were done, it's just the name that was new, but because any physicist or mathematician in many situations would use a lattice, a structure like that, in order to make approximations of physics or approximation of engineering or whatever, of fields. Essentially, it's just cellular automata is just discrete fields instead of being continuous fields like the electromagnetic fields or the gravitational field. All right. And other people have thought of similar things under similar names. Later, there was Konrad Zuse, about in the early 70s, that had, without knowing about phenomena, reinvented cellular automata. So he has structures called computing spaces, and so on. So at this point, I was at the University of Michigan, and I was, when I arrived there, they had a higher language at that time. We were talking about this, the 60s. And they had sort of a cellular automata thing on the screen. They went page after page, frame after frame, and so on. You have to wait between frames. I had taught myself some computing, and especially using the machine language, which is the most efficient that you can do in a machine, especially in those computers that were very slow and so on. And I redesigned a program that was about 10 times faster, and so I can just run cellular automata. And I started doing a whole thing of comparisons about between different cellular automata rules. I classified all of the rules that were possible in a certain situation, and then I realized that what happened, there were rules that just made a mess, like the children, they play with a chemistry kit, and after a couple of hours all of the bottles are open and all of the floor is dirty and there are smells and so on, but nothing that came. Others were classes where they were frozen, and others that seemed to be interesting. They were sort of open to development. And then these are the things that, by the way, I gave all I gave Stephen Wolfram all of the data and all of these things, and he more or less followed the same idea, but he followed it with, for some reason, with one-dimensional cellular automata. It turns out that Headland, a mathematical person that was dealing with what are called shift spaces, and were essentially a universal, one-dimensional way of doing physics, doing mathematics that way. He realized what he called that sandpit of higher dimension, that everything is fine in cellular automata when you do it in one dimension. The issues of finding things about invertibility, long length of cycles, and other things like that are very simple. The moment you go to above one dimension, then everything becomes undecidable. A lot of things become undecidable. So that, imagine when you go to 3 dimensions. Well, while I was doing this, I got the problem that I wanted to see how many orbits were closed in different rules, and how long the cycle was. And in doing this, I realized that there are certain things where there are not only cycles, but cycles with 3 branches on them. So because they are non-invertible cellular automata, if the rule is non-invertible, then you get into a path where there are merges between paths. And when there are merges, you can go forward well, but when you want to go backwards, now instead of a merge, you have a split, and you have more choices. And so I got interested. I mean, I realized, I was very naive at that time. I realized that there was this difference. And I started trying to figure out, how invertible cellular automata will work. Also for the reason that physics, both classical and quantum mechanics, presumes that the mechanism of the world is strictly reversible. Don't believe when people about quantum mechanics say, oh, quantum mechanics introduce an indeterminacy. The indeterminacy come, but not in the rule, but after the rule has been clobbered by some measurement operations that kicks the machinery. And of course, then gives, different. It's just like when you toss a coin, the coin goes flying in the air following strict physical rules. But when you then force the coil to be either up or down, or either head or tails, by just going like this with your hands around the coin, at that point you have some 2 possibilities. So I got interested in this kind of invertibility, and in particular, I was wondering about whether the universality of computation, like a universal Turing machine, could be done within a reversible medium. And my advisor, Arthur Burks, had as the conjecture that the moment you impose invertibility to a cellular onto a cellular automaton, then you lose computation universality. There was now a Russian guy called Aladiev who had written a paper saying that he had a proof that that was the case, that if you force invertibility, then you lose computation universality. But from what I was doing, I started figuring out that was wrong, that it could be done, you could have invertibility, you could have the cake and, the, what do you call it, the cake and eat it. You could have invertibility and computation universality at the same time. And so I started spending time checking, because there were two people that, that this Aladiev said that he had a proof of this fact that you lose computation universality. And I started reading the papers of this Aladiev, and the proof was not there, it was in some other paper that he had written, and he gave the reference, and I got this paper and I read that paper, and the proof was not there, was mentioned but not there for 2 or 3 steps. And finally, that was from Russia, and I didn't know how to go further. So a few days later, Arthur Burks come to my desk, and he said, "Tom, I just got a booklet from Russia by Aladiev. That may be, I don't know how to read it, but it may interest you." So what I did, I studied Russian until I could read that book. So I started reading it. And I was about midway, and there was a signature missing. You know what a signature is? The little things that you sew together to make a book. And so I was desperate. So I went to the end of the book and I started going triangulating from the end, trying to go to the missing area, the missing signature, to reconstruct the missing signature. It's like reconstructing an old, manuscript from centuries ago, that there are words or lines missing. And I finally figured out what the proof should have been. And at that point, Bert said, "Look, now you have the proof. You know that Aladiev proof is bullshit, and you have your constructive proof. And then so you have to say, well, Aladiev was wrong, I'm right, and go ahead and publish that." And so that is the way I entered into some sort of academic publishing and things of that kind. At the same time, I discovered, by studying these things, I discovered that there were 2 more people who were walking similar paths. One was Charles Bennett, very good friend of mine and of Norman Margolis here present, and Fredkin. I had written to Fredkin once, but never. He was too busy and very disorderly, and never replied. But then, when I got my Ph.D. with this thesis on cellular automata mechanics, where I also started seeing cellular automata from the viewpoint of relativity and from the thermodynamics viewpoint and so on. Well, when I sent my thesis to MIT, because I was looking for a job, and MIT was a good place, I didn't get an answer for a while, and so I was going to accept a very tempting offer by Bell, the Bell Laboratories, research laboratories. And actually, I had accepted that. But then I got a call from Fredkin, and Fredkin said, Tom, your thesis here, the theoreticians think that you are too practical, and the practitioners think that you are too theoretical, and they don't know what to do. Why don't you come here for an interview? And, we talk a little more. And I had sort of the idea that he was trying to decide to either support me or suppress me, because, when you do similar things, that's the thing in the academia. And so he invited me, presented me to Marvin Minsky, the inventor, in quotes, of artificial intelligence, and Jerry Sussman, another wonderful person at MIT. And he decided to hire me, and we started working. Let me see the time. And we started working together. He was very happy to have somebody that was there and could write, could read, could write a paper without so the moment I was there, I wrote a paper of something that I don't know how it came to my mind, and it was something that was that led to the so-called Toffoli gate. I will tell you a little more about that. But so when Ed, was a wonderful person, and in spite of being quite aggressive at times, that he wanted to, when he wanted something, he would get it. But he was also a very modest person, a very humble person in other way, and I respect him a lot for that. Okay, so he saw my paper and he said, Tom, you've written your paper, but you should write a paper with the things that I was discussing with you. And so I ended up writing this other paper called, what was it called? Norm, you tell me what was called the one with Fredkin.
Yeah, hang on. It was called conservative logic.
Okay, and conservative logic had, so all of my stuff and all of Fredkin's stuff rebaked in such a way to make it readable, understandable, and so on. And at this point, there was a time where more or less Norm Margolis joined us. And probably, Norm, you told the story of when you found that poster by Ed Fredkin, and you went to see him, and he said, no, the poster for this course was for last year. But Ed Fredkin got very interested in Norm, and Norm vice versa. And he joined our group, and we made a splendid trio at that point. Eventually was also Gerard Vishniak joined us. So we were with Norm once. We were looking at a very, very simple cellular automaton on a screen, and it went blip, and then you wait a bit, and then you get a different frame, a new frame, and so on. And it was impossible to see things in movement like that. So I got one of those cine camera that you put in airplanes in order to photograph a strip of terrain. And I used this camera to take all of the pictures that were coming overnight. We wait for a whole night to have a long string of frames, and then we played the sequence, and it lasted a few seconds, so it was moving fast. it was, you can see things moving and doing interesting things, but it lasted only a few seconds. And that was the time when I got the idea of making cellular automata, physical cellular automata machine, something that was a computer that will do only cellular automata, but doing it, dozens of times faster than with the computers of those times. And so this way were born the first cellular automata machines. And at that time, also, the people who were discussing, we sort of had played with the idea of invertible computation, came together. One was Rolf Landauer, who said, computation, whenever you have to erase a bit, you create a bit of entropy. And so you turn free energy into heat. But notice that he didn't say computation cannot be invertible. He said, but if computation has to erase a bit, then it will dissipate something. And it's good that he was, an honest person, and so he could say, he couldn't say no, it cannot happen, it cannot be done. It only can be done only in certain strict conditions. And so at that point, Fredkin, Landauer, and myself got together and decided to organize a conference called Physics of Computation. And I guess where we invited person by person, it was not as everyone is invited. I was, since I was the new one, and sort of the person who has to do all of the work, I ended up spending several months choosing, inviting a lot of people, and those were Feynman and Wheeler and Susek. Konrad Zuse is another inventor of cellular automata. And eventually we organized a conference, the centenary, no, the 40th anniversary of that thing was just a couple of years ago, I guess. Which was a wonderful conference where everyone was there. Everyone who was, everyone in the area was there. And it was a confirmation of the fact that invertible computation makes sense. It's not the best thing in the world. It pays a certain price, but it is possible. And that thing became interesting because people were getting interested in quantum computation. And Norman Margolis here was one of the first few people to write a paper on quantum computation. And the fact is that to do quantum computation, you need to run a quantum rule. And quantum rule means that the wave function evolves invertibly. And so there was a necessity to have some good invertibility in quantum computation. And in that conference, Feynman proposed the idea of quantum computation, but not the way they think of it now, because again, the quantum computation as done today is sort of iffy. It's not clear whether it will give everything, all that it had been promising. But Feynman, who had become a very good friend of of Fredkin, because Fredkin taught him computer science. By the way, Feynman had been the head of the computing group during the Manhattan Project. And at that time, computers were not people. Computers were young women who had graduated in mathematics and they didn't want to do research, but they were good at solving differential equations and solving them numerically by using one of those machines, you know, those machines that you turn a crank and so on, you know, the sort of a mechanical calculator. And by the way, my advisor Burks, at the time that people were excited about computers because they call them electronic brains, will start his lesson say, "I married a computer," and people say, "What does he mean?" Okay, and well, because his wife was one of these computers. All right, so Feynman's idea was to have some piece of a mechanism that is quantum mechanical and combine it together with an ordinary computer in such a way that this computer will essentially use that whenever he wanted to do something quantum mechanical, and then we'll combine it with other things. It wouldn't do all of that, the computation, only the critical computations in quantum mechanics. And in fact, that works very well today, that you can simulate a lot of physics with quantum mechanical computers. So the things that work, and I believe exist, but there are other things that I'm sort of a bit iffy about in quantum computation. By the way, Norman here was the author of a seminal paper that essentially proves that the amount of energy available gives the upper bound to the speed of computation. Oh, no, so not only the speed of computation, the speed of everything, the speed of evolution of a physical system. The maximum speed is bounded by the energy available, not the energy consumable. Wouldn't be consumable. It's just like you know, when you have a pendulum with no friction, it has energy, and with more energy will move faster, but it can go on forever and ever. So it doesn't have to produce entropy to dissipate if there is no friction. Let me see what time it is. It's 12. I will speak a few more minutes and then I will leave time for questions. Is that all right for you?
Yes, sir.
Yes, because I'm interested in hearing the questions, and you probably oh, well, there is a whole story of the idea of making a little homemade cellular autonomous machine eventually developed in better cellular autonomous machines and better ones. And finally, Norm and I got a grant from DARPA. I guess at that time was for $5 million, that today would be about $15 million and so on, to develop a really cellular autonomous machine with a very good architecture. And we developed it. We spent a lot of time down to the last screw of design of this machine. And eventually, however, that the war, what was it called? Well, the tension with Russia has decreased enormously, and so there was no more need felt to have a lot of parallel computation and a lot of cryptography. And so eventually this machine came to, well, eventually the lab for computer science and the artificial intelligence got dissolved, and then they were reconstructed a few years ago. And so this beautiful machine became obsolete because hardware gets obsolete very well, very soon. So we'll not make the mistake of making another wonderful architecture machine, but we will make a softer, try to make a softer machine, a softer cellular automata engine that would be, computers now are extremely fast, have enormous amount of memories with respect to the time when we did that. And it would be nice to have some sort of group that gets interested, and maybe somebody of your students in India would be interested in collaborating in trying to have a computer like the one that I'm using here. It's an Apple Mac that could do wonderful things if we were programmed the right way, and to have something available to everyone in order to, if you do not have a machine to run cellular automata, it's very difficult to guess what they can do. All right. The final thing is that this story of the invertibility, the Toffoli gate came from the fact that was the paper that Fredkin told me, Tom, you've written your paper, now you got to write my stuff. Instead, eventually, what happened is that I was interested in the fact that many proofs of invertibility of computation were for computation that is discrete, but the physical world seems to be continuous, and so certain things cannot happen in a continuum gate. Suppose that you have a gate with 3 inputs and 3 outputs, and not all continuous gates like that can be invertible, even if the discrete part is invertible. The equivalent of the Toffoli gate in digital was proposed by Quine one particular gate quite many years ago. The fact is that there is an issue of topology. If you want to go from 0 to 1 and to the 2 states of a bit, ideally you can do it in just one 0-time step, but in physics you will have to do it continuously. Well, but you have to do it continuously, not moving back and forth on a segment. My discovery was not back and forth in a segment, but by going around a circle with a crank. So there are 2 ways that you can go from 0 to 1 and 1 to 0. And that's a different topology. So that was the novelty of that Toffoli gate. And eventually, I hadn't called it Toffoli gate. Then Feynman, however, discovered it. And he saw that it was wonderful because it was quantum ready. It's just replaced the circular crank into spherical ball. What is it called? The sphere, somebody's sphere, okay?
Block sphere.
The block sphere, because that is where the quantum state runs around the block sphere. This is for just one-dimensional thing, but you can do it for more dimensions. And so eventually it became there was a meeting. I'm very ignorant of quantum mechanics, I have to confess. And so somebody else, however, found that this gate would be a very good primitive for quantum computation. And there was a paper of about 10 people, including Shor, including Norman Margolis, including all of the people at that time were interested in quantum computation. And somehow they invented the term Toffoli gate, and they used it 20, 30 times in that paper. And the thing was Kristen, it was nice for me, but I'm glad that they could use it and use it well. Okay, I'm finished talking about the merging of myself with all of these other people and other places and so on. And I would like to have some questions about all of that I said, and bad questions and good questions, as you wish.
Okay. Thank you, sir. So I believe, yeah. Okay. Norm Margaret. Norm has raised an hand. Yes, sir, please.
Hi, Tom.
Hey, hi, Norm.
So, two things that I think would be fun for you to mention or to talk about. One is just what Charlie Bennett's contribution was to the idea of reversible computing. And the other is just your view on reversibility and entropy. So I don't know if you could see.
Yes. Okay, well, Charles Bennett is a wonderful person. I mean, of all of the people that I know, except maybe Norman, is a wonderful scientist, and in a lot of areas, it made a lot of discoveries. When he was renting an apartment in my house in Cambridge, he was developing the idea of quantum cryptography, and he knows everyone. And now at this point, he spent his time going around the world giving conferences because everyone giving lectures, because everyone loves the way that the things that he does that have been very original. And his quantum, I use cellular automata to study, to understand the story of invertibility. And he used Turing machines. And Ed Fredkin was used digital circuits. So there were three people that were dealing with the same issue with three different approaches that then ended up being concurrent. They were all interchangeable, just like that Turing and Post and cleaning. They were discovering the same thing at the same time. And let's see, what was the other thing? Bennett, and then Norm?
Entropy and reversibility.
Okay, yes. I have a paper that has a very strange story with arXiv, because after I sent it to them, it didn't come out. And I called them and I said, well, we deleted your paper from our archives, archive, that thing for pre-publishing. And he said, well, if you want to do something, maybe you should give a list of your career and your publications and so on. It's just like saying you are a crank. And because I had, I assumed that some human or artificial intelligence was vetting those papers submitted to archive. And they are so many that probably they had some quick method, some quick sieve. And I had put very early in the paper a number of myths about entropy. And somehow some people started rending their clothes, so to speak, by saying that I was saying that these are myths. And actually, instead, that those myths are myths. So it's called entropy, question mark, honest, exclamation mark. And it deals with just one aspect of entropy, but deal with what kind of things entropy is. And it says that entropy is not per se something that has to do with physics. It can be used for a lot of other things. It's a mathematical thing. And you cannot, strictly speaking, speak of the entropy of a system. You have to speak of the entropy is a property of a description of a system. So you want to read and tear your own clothes if you prefer. And but as Norm says, invertibility is very useful because it's just like a pinball machine that lasts for a long, long time because it has long, long orbits, and it doesn't waste any piece of phase space. If you have an uninvertible structure, then after a while, most of the phase space has been swept out of the way. And so that is one connection between entropy and invertibility. And what, I don't know, was I clear, Norm? What do you think?
Well,
you say something about this.
well, I think we often have arguments about this because your point is that entropy is just part of mathematics. It's information, and information shows up everywhere.
Yes.
And I always try to argue that it's objective in physics, but you're pointing out that's only because it's a very special situation and large scale and so on, and that entropy. You were giving an example when we were talking the other day that people might think that if they invented counting, they might think that counting is something that applies to sheep or something. But in fact, counting is a very universal thing that applies to everything. And your view is that entropy is like that. Entropy is a very general property because information is so important in the world. And people think it's, people who think it's very special for physics, that they have a too narrow a view. And anyway, I don't know if you want to say anything more about that.
Well, no, I agree with this. I agree totally with this. It's an extreme generality that can be used very usefully for physics, in physics.
Yeah, and maybe I should also say that all these ideas about trying to understand physics as computation, these are things that were largely inspired when I was working on it by Tom. I worked much more with Tom than with Fredkin. Fredkin was up in the clouds and he was changing the world and doing a million things. And Tom and I were working in the information mines, the mines at the bottom of the information mechanics group, actually trying to, make practical models of things and, little progress on things.
Yes, but Fredkin was very good because he had the courage to start this, to organize this conference with Landauer and Bennett and so on, and essentially he broke a barrier between what we were doing and what the world was willing to listen to.
Yeah, I mean, he was the first to have both the insight and the courage to say that there were deep connections, or at least one of the first, and certainly the first that I knew of. Anyway, I should perhaps let other people ask some questions, though.
Go ahead.
Yeah. Any questions? Okay, I have one query regarding this entropy. I was reading your paper, that entropy honest, that one. So there you are talking about this randomness and random number generators. Why a number cannot be random? Rather, we should talk the generating algorithm as the random one. Like it's the property of the algorithm that's output is a random number. So what is
that is absolutely right. Imagine this idea: that is a teacher that that doesn't want to read the paper, and so he tells his students, make a column of the integers 0, 1, 2, 3, and so on, and then make a second column where you put the squares of these integers. And then you make a column where you mark all of those integers that are even. And then you make a column where you mark all of the integers that are prime, okay? And then you make another column where you mark all of the integers that are random. Okay, now can you imagine the absurdity of the thing? Is 7 random or not? Or 17, is 17 more random than 7? It's not the number that is random, it's the algorithm that is random.
Yes.
And this is the same thing that I'm saying about entropy. Entropy is a property of the description. Then now how you use that description is another thing. But it's not a property per se of the system. Per se is a property of the description of a system.
So I'm just wondering, what is your notion, what is your comments on the idea of this true random number generators, which generally works on the principle that it will take some physical source of noise, and then based on that it will calculate the numbers. So do you call that a true random number generator, or you will not you will not go with that notion of true, something as true random?
Well, you just said it. The property is the property of the algorithm, not of the number. And an algorithm to do what is could be called a random numbers. First of all, must be given enormous number of choices, and not waste many of them, and then do it in a different way every time. What else can you say? Essentially, it's just like when you shuffle some cards. Okay, if somebody was watching you with a telescope with high resolution, they could see where the cards go one after the other, and after that they will take that deck, close their eyes, and somebody says, get the ace of spades. You will close your eyes and you will pull out that, but just flipping through the deck, you will pull out that ace of spades, because you've seen exactly where it went. Okay, so for you, that the deck is not random. And so it has to do with your knowledge. So it's a way of having something where it's impossible to have some, very difficult to have very detailed knowledge. So you give up and you accept the randomness.
Okay. Okay. So I'll let, yeah, now Marvelous. Yeah, now please go ahead.
Just one thing that I think that you probably meant to, I'm sure you meant to mention was, when you said that Landauer was honest and, he said you needed to have reversibility to avoid dissipation. As far as I know, the first person who actually showed that you could do computation reversibly was Charlie Bennett. Is that right?
Well, I think, I don't know exactly of the times, because in my list that I have here was probably it was a little. He had done that with using as an instrument Turing machines, so clearly had solved the problem of computational universality for an invertible cellular automata, for an invertible Turing machine. He didn't put it that way, but clearly he was, right with that finger on the pie.
But I guess you were doing things in your thesis at about the same time, and Fredkin, who never published anything, probably invented the idea around the same time as well.
That's right.
Okay. And of course, mathematicians were doing reversible things, and hash functions were invertible and things like that. So I mean, the importance of invertibility in computation, people had hints of it already.
Well, you imagine that group theory, it's all about invertibility.
Yeah, sure.
100% invertibility. That's why I said invertibility is a gift, not only to physics and cellular automata, but also to mathematics.
Right, because it's so helpful if you can have invertible functions. That there's so many things you can do with it.
Yes. All right. I would say that if there is some interest, I'm sort of old enough and busy enough that I cannot, and ignorant enough of really the aspects of computation in or programming in new computers, and all of that, the hardware and the memory and the tricks and so on. But it would be a nice thing if there were some people or some sort of a consortium devoted to making a universally available, highly efficient cellular automata machine, and especially something that would be useful for physics. So it would be an invertible, it can be used also as an invertible cellular automata machine. Because it would be very useful with so much storage and so much speed that we have now. We can reach, I'm kidding now, but I'm not kidding. You wouldn't be kidding in 10 years or 15 years to essentially to have a system that has that Avogadro number of pieces, and they can be studied both microscopically and macroscopically. In other words, see where the edge between microscopic knowledge and macroscopic knowledge, how it may advance, so that at a certain moment you can see the same thing in both ways at the same time, and so explain certain facts of microscopics of condensed matter and other things like that. So it's not, the time is not ready, but if you don't prepare some approaches to try to bite that particular cake, you will never do it. So I was wondering whether, and anyway, it would be a very useful thing for everyone, because all that I see around is little pieces of program that have Conway's Game of Life, and you can do anything you want with the Game of Life, but you cannot do anything else. You cannot program it, you cannot instruct it. And so if there was, I have a student of mine made as a PhD thesis a software cellular automata machine that actually, but now I have, but it was at the time where um, um, well, let me think, where Python went from Python 2 to Python 3, and where NumPy, which is the numerical thing of Python, went to, it was new, and it was eventually enriched enormously. And so I froze this little machine in a chip for Raspberry Pi. It's the only thing where we have a workable, it's not so fast, but a workable implementation of the architecture that we had, Norm and I had for CAM8, which is a very flexible architecture and a very orthogonal. And so if there were some students that either for their training or for their greed of selling something, or for as a thesis or as a project or as a group, could get together and squeeze the most that they can from the always marching forward resources that we have in software, to have cellular automata that you can make a world out of. You understand what I'm trying to say? So I would be happy, and probably Norm would be happy to give some advice, to give all of the material that we have about the CAM8 architecture, to transform it into a software thing using the best of software that is available at the moment, on the best hardware that is available at the moment.
Okay, so
I'm sorry.
Raised hands. Can you take some questions?
Norm, maybe you're a bit too skeptical about this suggestion, because you're afraid that if somebody starts, you're so generous that you will spend a lot of time helping, directing, and solving, and so on, that you don't want to step into that river. But I think, and I'm myself, I don't know that I will be able to keep such an organization, but I think it would be it's very desirable.
Well, I could make one comment.
Mm.
I think that I mean, Tom and I have slightly different visions of the purpose of doing some software implementation. I mean, I think for both of us, the idea of being able to play with this stuff in sort of the kind of way that we were able to play with it with hardware, people, there are a lot of cellular automata programs that people have, and they're rather specialized, and it's very important that they do game of life very fast and things like that. We had a viewpoint that came from physics. We wanted cellular automata that were good for simulating physics. And so a lattice gas, basically everything interesting in physics can be done with a lattice gas. And so that kind of architecture allows you great generality to do things in physics. And also it's something, to me, the great attraction of providing a tool like that in software is that you can make it really fast in software, but it can be, literally, hundreds of millions of times faster in hardware. You barely, even a really good software implementation will barely give you, a glimpse into what, the possibilities. And so I think doing anything in that direction would be a great benefit to, pushing a new direction in computation, which, when we made our cellular automata machines, we were sort of a bit slow, and then, the project got canceled because DARPA didn't think it was a good idea to make hardware. But the whole point of our project was to let people experiment with this new sort of band of the computational spectrum. And what ended up happening with the whole field of like lattice gas, molecular dynamics, lattice gas simulations of physics, is people quickly started making like floating point lattice gases, Boltzmann equation and things like that. And that was the practical thing, because that's what most of the hardware in ordinary computers is devoted to. And so as long as
real number module.
Yeah, because your floating point numbers become equivalent to like averages over many cells of a big patch of your lattice gas. That's more or less the way they treated them. And so, what ends up happening if people don't have the right tool to play with these things, and they want to do something fast in their computer, they quickly migrate over to something that has like floating point numbers and things in it. And pretty soon it's not going to be something that you're going to be able to make 100 million times faster on hardware anymore. And so the specific thing I think that we would like to try to encourage, in some sort of software, is playing with lattice gas type things and make it sort of fun enough and powerful enough that it encourages a certain direction which might not naturally occur to people who have floating point hardware in their machines anyway, right?
Well, look, think of this. Von Neumann just got the idea of having set-free production. He wanted to do something about sort of biology, so to speak. And even though he was a very good physicist and extremely good physicist, he didn't put any physics in his cellular automata. And the same thing, and so his machines, his rule was not invertible. And the same thing for Conway's Game of Life. It's very nice, so you can play for it for a few minutes and enjoy it, even prove that it is computational universal, which is some sort of a lie, because in order to do universal computation, you have to clear the entire world, the entire world to zero, to something predictable. Otherwise, your computation will, the moment it finds a pebble, it will stumble. And so it's amazing that Von Neumann, who was a great physicist, just left cellular automata orphan, first by not finishing it and letting Burks finish it, and second by not making them invertible so that they would be a reasonable model of physics. I'm finished with that.
Yeah, I mean, one of Tom's famous papers was cellular automata as an alternative to, rather than an approximation of, physics. I don't remember the end of the title, but that was a theme that he taught me about, and that we pursued in the information mechanics group. And I think we'd like to somehow push that out more into the world.
Yes.
Okay, yeah, I'll take the question. Shukanta sir.
Okay, thank you, Tom Toffoli as well as Nomma Wallace. So my question is related to your CAM, Cellular Automata machine. So I was listening to your discussion and I have some point. See, when CAM came into picture, Cellular Automata machine. So as I have read, at the time I was not there, but I have read that it was a actually big hope that Cellular Automata can be implemented in hardware and we can get Cellular Automata machines. However, in 90s and after 2000 also, we didn't see much progress in developing cellular automata machines. Although, for example, we in India work on cellular automata technology, we have proposed some kind of cellular automata hardware and some kind of programmable cellular automata were proposed also. But in true sense, the cellular automata machines which can do some kind of computation and can do jailbird computation, that kind of dream, that didn't, that was not realized actually. So what was the reason people didn't think much on developing, realistic cellular automata machines, which can be used by everyone? So that is my query, to both of you.
Well, one big loss of the original formulation of cellular automata is that is called cell. That is that each side is a box containing information, and then he has to look at the neighboring boxes, and many different boxes will look at the same box and vice versa. So there is information that gets reduplicated and so on. While instead the approach of CAM8 was a step that is space-time event processor. The events are not places where there is information. The events are gates. The information is in the wire that connects these gates. Think of the way relativity, special relativity is described. You have events and you have rays of something that is moving at the speed of light between events. So the information, if you put the information in a box, then you have to make a lot of duplicates. Instead, in this approach, each piece of information is only in one place. When it hits a gate, gets transformed, and the same amount of information comes out from the outputs. So that is an important difference. It's like making a table of numbers, and when you do the next column, you write the difference between the points. So you need a table that doesn't, instead of having just points, you have what is between points. The information is in the arcs.
I could try to say something about the failure of cellular automata to take over the world, which Tom and I had great hopes for, especially after people showed that lattice gases might be useful. So there was a moment where there was some excitement. We did commercialize Tom's machine that we'd been using, the CAM6. That was a commercial version of the machine that Tom had come up with that was very good for playing with cellular automata and seeing that they were fun things to play with. And it was something you could stick in an IBM PC, and it let people play with this kind of TV into other universes, right?
Oh,
You know,
let me interrupt you a moment. We sent one to Feynman. He was in California at that time. And he and his wife was planning to do some vacation in Mexico. When he got this, he started playing with it. And then he said to his wife, you go to the vacation and I want to play with this.
Yeah.
And we have one copy of the instructions for this machine annotated by Feynman saying, what does this mean? Why do you why do you do this way? Why don't you do this, that, and so on? But he motivated all of this saying, you give this machine to a lot of kids and they will invent a lot of things.
Yeah, so it was something that even that, the first cellular automata machine, making it something commercial was something we thought would have a big effect on the world. One of the problems there is that we had one of the best computer designers in the world who designed the CAM6 machine for us, the commercial version. Unfortunately, his partner was one of the worst managers in the world, and they had some other project they were making money from, and he never got around to like ordering the parts and making the things. And I think they eventually made like a few hundred.
It took 3 years to do that. So.
But there were like thousands of people who were trying to get them, and we made the great mistake. We didn't, we were very naive. And so, because these people, the person we were working with was so smart and so on, and everybody was so happy, we did, we let them own the design that they made for us that we paid for. And then when they didn't produce anything, we couldn't give it to somebody else to just make, right? And so, the MIT lawyers who wrote up these contracts, they should have known, that you write contracts for when something goes wrong, not when things are all good, right? Anyway, but to the deeper question about why the cellular automata didn't take over the world is, the kind of commercial uses for cellular automata are things like, computer vision and so on. And those are very specialized, and those can be done pretty well in software or with, there's a little bit of hardware assistance, FPGAs or whatever. The real use to change the world was cellular automata as models of physics, or cellular automata sort of virtual reality, a bitmap instead of, the way that people do, 3D simulations these days with vectors and so on. And to make that jump, I think you needed a better intermediate step, at least at the time we were working on it, than just software simulations. And so it was important, there's a chicken and egg problem. If you're saying I can make this 100 million times faster, well, you can't simulate 100 million times faster on your computer. It's hard to get applications that really are exciting enough on ordinary computers to make the thing happen. And so I think we kind of failed the world, when our project got canceled and we, that line of research, it also took us too long. And by the time we had even our prototype machines, people were already using the floating point units in their ordinary computers to do something that was pretty good. And so the lattice gas application, which was the thing we thought would take over the world, they were able to do that well enough on ordinary parallel computers with lots of floating point units, that the enthusiasm to transform physics with discrete models, that kind of died down. And I think it's still true that there are applications that would transform the world, in that format. But we'll have to convince some other people to make some cellular automata machines. It's their turn now, right?
Okay, we've done enough for ourselves.
Okay, you have great hope on lattice gas automata, I understand. So what is the future then? What do you think that in future it will be commercially successful, so that automata machines is possible to do?
So the big thing, I gave some examples in my talk, but I'd say there's two applications which I can think of, which I think people would be very excited about. One of them was sort of logic simulations, because you can virtualize them. The cellular automata machines we're talking about, they don't actually do everything at once. And if you concentrate them on sort of a wavefront of the computation, there's things that look like cellular automata that are organized in space, but which you can do thousands of times faster. So very irregular things, including things like neural nets and so on. At the time when we made these cellular automata machines, in the 90s, we had estimated that just that architecture, the CAM8 architecture, would already be able to simulate something, with enough memory and so on, simulate something of the complexity of a brain, sort of at the millisecond rate that signals work in the brain. And today we've got another 2 or 3 orders of magnitude of actually, even then there were more orders of magnitude, because we could have made things directly with logic on memory chips. So I think that simulations of irregular things, simulations of logic circuits, simulations of neural nets, simulations of simulations of discrete physical models. Part of the problem there is that my view is that classical mechanics is essentially a discrete model if you take quantum mechanics into account properly. And so macroscopic things should be able to be simulated rather well with a cellular automata machine. People don't normally think of classical models as being fundamental models of physics, and something that you can do on large scales. It may not be exactly what's happening at the most fundamental scale, but they are very realistic at a certain scale. I think there's all sorts of simulations of large scale simulations of physics, but they're done in a way, very fine. They're very fine grained and very large scale. And as soon as people start
very high speed.
Yeah, as soon as people start doing fine-grained models and they need a large scale, they immediately, on present-day computers, they want to take averages over some set piece of the thing, and use their ordinary computers and floating point units and so on. And so I think you really need. It's hard to make that jump without hardware that makes it much better for them to do a much larger scale with simpler dynamics and so on. So that's, physics, just physics, as I was calling it, virtual reality simulations of physics, because you can do virtualization, you can have the light and so on be done virtually as a wavefront, so that that part is happening very fast, and the high resolution of real physical systems, on one chip with, high memory bandwidth and so on, you could do a simulation of like the harp in a piano, a full physical simulation, with the, just using the some sort of a scan of the piano at a very fine scale, and do a bitmap simulation that would sound like the piano in real time. This is the sort of thing that people wouldn't even think of doing, because it's too much of a jump from what people are currently doing. I think that you have to get people excited about the possibilities, that they'll do something now that maybe isn't quite practical, but is very interesting. And sorry, you wanted to say something, Tom?
Yes, what I'm saying, compare with artificial intelligence, especially that what is it called, GPR or whatever, that is essentially GPT, a literary way of collecting pieces of paper that has been written by somebody and mixing them together and so on, or photographs. The fact is that this is, for me, that is not artificial intelligence. It's just copying. You go to a test and you have things written on your hands or on your cufflinks or something like that, on your cuffs. What is missing are two things. What is mostly missing? One is the cause and effect. And there is a lot of progress scientifically by Julia Pearl about cause and effect was ruled out of statistics for many decades because they thought that it doesn't have anything to do with statistics. But okay, so now essentially we can do cause and effect as legitimate science. The second one is consciousness in the sense of self-defense and self-reproduction. If you read the book by Daniel Dennett called From Back to, was it, to bacteria, from bacteria to back and backwards, and it shows that every structure in facing biology and so on is just interested in having an identity, having a sort of a purpose, and if the purpose is to replicate itself, that is the most interesting one. So it seems to me that with cellular automata, you have cause and effect essentially clinched in. There is no way that you can, you're not just looking at an old newspaper and collecting all of the clippings and so on, and then they say, this is what things are. So there could be an alternative to simulating or making or describing a world which includes evolution and cause and effect.
Yeah, just one other comment. I'll try to be quick. Is that when I was talking about physical simulation, maybe one thing we could get people excited about, which I'm trying to work on a bit, is if you can think of classical mechanics as fundamental at a certain scale, because it has information, and if you do discrete finite state models of classical mechanics, they have information that can be simulated efficiently on computers and on hardware and so on. And if they have a connection directly to the ideas of energy and momentum and so on in physics, they kind of act as a intermediate stage between fundamental physics and the large scale of things like general relativity and so on, which that's something that's hard to simulate, and it's hard to understand its connection to quantum mechanics. But part of its connection to quantum mechanics is information and conservation laws. So I think that these kinds of models, you might be able to get people excited about them, and maybe even for somehow get people to make machines to do these big simulations if they thought they were doing fundamental physics and were learning something about the connection between the most macroscopic things in the universe and the most microscopic.
Yes, yes.
So somehow in the same way that the discovery of lattice gases caused a spurt of interest, maybe the discovery of some fundamental connection that you're going to actually learn something real about the universe by doing these models, that could encourage a new renaissance, right, of this stuff. And maybe we'll have some real cellular automata machines. Okay, so I think people had questions. So go.
Yeah, I'll take a quick
Yeah.
question.
Thank you. Thank you. So hope for the best. Thank you.
Yes, exactly.
Hope for the best.
We'll work on it.
Uh,
Like they were saying in the animal farms, the horse that always say, well, yes, well, I will work on it. I will wake up in the morning early.
Okay.
Yeah.
Hello, sir. My name is Supriti. Actually, I am interested to know that just you told that von Neumann, when introduced the concept of self-replicating machine, and then Bach introduced cellular automata, we have the cellular automata that were non-invertible. Now, my question is, if we have all the, suppose that I have all type of non-invertible cellular automata, then how far we can go? That we do not know all the invertible cellular automata we have not introduced, and we have all the non-invertible cellular automata, how far we can go?
Well, it's how far. Once I made I have a one-page paper where it says, take a system with a finite number of states and see how many dynamics it can have and how many dynamics that are invertible. And it turns out that you can essentially, if you take the logarithm of that, that is always a constant strip that comes from that gives you that you have many fewer choices for invertible ones, but there is some sort of a constant rate of doing that. I will have to go through my papers and fish it out. It's just a very, very simple thing. Just count invertible and uninvertible rules on that system.
Was that your question?
No, it was, I'm saying that you can count how many rules you have at all in your, suppose you have a finite cellular automaton, and you, how many rules you can have on it, and how many invertible rules, and that logarithmic, the difference is not very large.
Not very large, but in general, in any finite system, we have seen that number of reversible or invertible rules are actually very small in compared to the number of non-invertible rules. That's the general case. So number of invertible rules are actually very small.
Well, that's
Isn't it?
Small, but what I'm saying, logarithmically, it's not extraordinarily small.
Sir, can we know the title of this paper?
You're begging for questions from somebody else?
no. She's asking about the paper you mentioned. She wanted to know the title.
Well, look, I don't even know whether I published it. I have a collection of briefs. I met it again a few weeks ago. I didn't even know that I had it, and I would send it to you.
Sure, sir.
Okay, so the
Thank you.
one last comment I want to ask from you, that is, I was just going through your discussions on what is computation, how does nature compute, the panel discussions, and the book chapter that came out of it. So Norm was there, you were there, Ed Fredkin was there, Stephen Wolfram was there. So we were discussing about whether the universe is a computer or not. So I'm just asking whether that same view persists still now, or your answers have been changed. And what is your view on on Wolfram's physics project, where he is saying that universe is doing computation, but it is not a cellular automata; it is some kind of computation. So your comments on this?
Well, I really didn't understand completely the question of who's doing that. And
Is universe a computer?
yes,
This question was asked to you before also, and in a panel discussion, which came out as a book. So you gave some answers there, and Stephen Wolfram was also present at that time. So and now he has completed the physics project, Wolfram's physics project, and there is some contradictory view on how you whether the universe is a computer or universe is a cellular automata. So well, I generally I want to know your comments on what do you think about this physics project of Wolfram, and your view on whether the universe is a computer or it is doing computation only, or it can be modeled by an automata, not necessarily a cellular automata. It can be modeled by an automata only.
well, I mean, I wouldn't speak about universal computer. It's computational universal computer in that sense, that somehow can do everything. And you know, a very simple cellular automata machine can do everything, but at an enormous cost in time and space. And it's hard to tell. You can have a universality and pay a lot for it.
But I think she's asking though whether you believe in Fredkin's thesis anymore, or whether you ever did, that our universe is a classical cellular automaton.
There's no evidence, you know, it could be. If you find that cellular automaton that simulates the universe, then the answer is yes. Otherwise, it could be something.
I was asking about
vaguely,
also
yes,
regarding this.
It's a bit to think of quantum mechanical field theory.
Hmm.
You know, where it's something like that.
Okay.
I
Okay.
I could make one slight comment, which is just
Please.
that you know, the direction that somehow there's some classical computation going on. You know, I like that direction. You know, if you do something that's sort of equivalent to sort of simulating the many worlds of quantum mechanics, that strikes me as just another way of you know, if it's equivalent to the normal view of quantum mechanics, then I'm not sure it tells you something new about how the world is just a computation. Because if it's a computation, but such a large one, compared to what we're actually seeing in our world, you know, maybe the universe is that way. That might well be. But you know, I would like to see something simpler. That's all. So you know, I'm always, Fredkin was always bothered by the idea that, you know, physics is sort of magic. You don't need, you know, you have computation, but you don't need a computer, right? You know, there's all this information transformation and classical information transformation, but you don't have an idea of, you know, how is it that, you know, what are the operations, where are they being done, and so on. And in physics, you learn not to ask those questions because, as Feynman once put it to me, you know, the people who ask the question, you know, how can the universe be the way, you know, that it is, you know, the quantum mechanics be the way that it is, their careers all went down the tubes, he said. And he was worried about me because I was interested in these questions. He says, Margolis, you know, I'm worried that your career is going to go down the tubes. And so, you know, I think that you know, nevertheless, it's a question that, you know, anybody who's ever tried to, you know, study quantum mechanics, they have that question: how can it be this way? And you know, so I think that Wolfram's thing brings, you know, physics closer to some sort of model with this classical computation underneath. But I don't think it answers that question, at least not for me, for how can physics be that way, without just sort of replicating the whole thing, the way that we understand it now, but just in a sort of a digital form. But I may be giving his endeavor short shrift. I haven't studied it, and there's probably a lot more content there than I understand, and it's probably a lot more helpful in bringing things more together.
Okay, so thank you, Professor Toffoli, for sharing your time, your knowledge and insights with us. Thanks a lot for the 2 hours of very insightful talk and very interesting discussions. And thanks to Norm Margulis also. Thanks a lot for joining us and making it like a panel discussion. So we enjoyed a lot. So as our next speaker has already joined, so we have to move forward to our next session with your permission, if you please.
Okay, and I would like to thank you for inviting us.
Yeah,
and
thanks.
for your patience in listening to me.
It was a pleasure for us. We'll be liking to listen to you again once, if you have time.
Okay, well, I will try. Now I've just settled again in Rome, and it will take a few weeks before well, I think that I will go into research again soon. But I've been writing a book on evolution, always in my mind, because I was too busy with my hands with other things. And I would like to get rid of it to write it before starting a new project.
Okay. Thank you, sir. So let me go on and invite our next speaker then.
Okay, splendid.
Yeah.
Thank you very much.
Thank you, sir. Thank you for coming.